Welcome to one of the last talks. My name is Thomas Fan. I'm a staff software engineer at OnSite Labs. I'm also a maintainer for scikit-learn, which is a machine learning library in Python. Today's talk is about parallelism in numerical Python libraries. It's quite a big scoping talk because these are all loaded words. Parallelism is a loaded word. But we're going to narrow the scope a little and talk about a specific piece of it here. So when I mean parallelism, I mean CPU-based parallelism. So no accelerators like GPUs. That's a totally different talk. It's a big topic. Also, I mean things that run on your laptop are a single node. So no multi-node ideas in this talk, except for like 2 slides, which I'll cover. And with an emphasis on Python. This is how Python libraries now parallelize their code. Like these are the libraries you use today, and how do they take advantage of all the cores on your computer? Because all our computers have multiple cores. It's the thing in 2022. So a very high-level overview of this talk is we have 2 main ideas. We have configuration and implementation. Configuration is how do you control the libraries you use, and as in how do you control the number of cores library uses so that you could scale up or scale down for a library you have. So that's very important for end user. And there's also implementation is how does these libraries actually do it? So there's 2 worlds here, and I'm going to cover both of them. It's very ambitious. But we'll start off with something simple. NumPy. NumPy has some parallelism, and I'm going to start off with a demo with comparing add and matrix multiplication. So how many here use NumPy or know of NumPy? Cool. We're in PyData. I know I'm at PyData right now. I'm going to do a quick demo on add and matrix multiplication. On the top, I have a Jupyter notebook. I'm using NumPy's cool new generated API here to create a random matrix of 50,000 to 10,000 array. On the bottom, you can see that I have 10 cores on my machine. This is on my local machine here. On the bottom, it's how much. It's when the bars are full, that means my cores are being used. All right, so it's monitoring my CPU. Here, I have a quick time it command with empty.sum. And my question I want to ask here is, who thinks that this will be parallel? This will take up all my cores. Cool. All right. So that means that when I run this, you can see that it will just use up one of the lines will light up. Right? So it's a single threaded operation. The other one is matrix multiplication. It's basically addition with some multiplication. Right? It's not that too much different from addition. I'm going to create a matrix here that's compatible with X that I created before. And if I do this, how many people think that matrix multiplication X and Y is parallel? So yes. So this is parallel. It uses all my cores, and it's taking advantage of all the compute in my machine. I found this, when I first saw this, I found it surprising. Like when I first encountered this API. And there are many questions you want to ask when encountering this, and we're going to cover a bunch of them. And as we'll start off with, when is NumPy parallel? Like we saw that add is not parallel, and matrix multiplication is. It turns out NumPy linear algebra, everything in NumPy linear algebra is parallel, and the way you notice is going to the docs. Like the API doesn't actually. It's not explicit. You have to go to the docs, linear algebra, anything under this page is parallel. So that's how you know. Next question is, how is linear algebra implemented? And this is, NumPy itself doesn't have these linear algebra routines. It dynamically links to libraries like BLAST, to libraries that implement the BLAST API, like OpenBLAST and MKL, which is Intel's math kernel library, or Bliss, which is another one. The thing about and each one, and the BLAST is a stable API it's a stable API that defines linear algebra routines. the question here is, each one of these have different performance characteristics. The Intel one could most likely favors the Intel GPUs. So depending on which blast you have, it may have different performance characteristics. So things that run fast on your laptop may have different performance characteristics than on a server. How do you know which blast you're using in NumPy? There's this cool library called threadpoolctl, which you could run this on a command line. And what this gives you is the configuration. And if it's using OpenBlast, if it's backed by pthreads, which we'll get into later, and how many threads it's using. If it's MKL, it will give you something like this. It'll tell you that's MKL. So this is a quick way to diagnose which blast your NumPy is using. Now, how do I select which blast I'm using? On CondaForge, it's easy. You could just switch by one of these commands. There's many different blast implementations. And on PyPI, you're only stuck with one. You have pthreads, and it's backed by OpenBlast. Now, remember one of the key points is configuration. How do you configure matrix multiplication for parallelism? There's two ways, environmental variables and threadpoolctl. Environmental variables, there's a whole host of them. There's many flavors of this. There's OpenBlast numthreads, MKL numthreads, OMP numthreads, which if your backend is built on OpenMP, that's what you use. And there's quite a bit. You have to know of them. There's a lot of environmental variables. I find the easier approach is you do threadpoolctl, which is a Python approach to do this. So this you don't have to, you can see that here. It's a context manager. You can see that I'm saying blast. You don't have to care about its MKL blast, open blast, it just does it. It understands which blast is loaded and it configures it the correct way. You could do it as a context manager. You could also have it globally. So that's a very useful tool. A common question I think about is how would I parallelize that? Can I do it? There's many tools for this. Numba, have you heard of Numba? Very cool just-in-time compiler. Cython, PyTorch. I'm going to show two of these because Cython is I'm going to show Numba and PyTorch very quickly as a quick demo. So how do I parallelize that? Numba is a just-in-time compiler. You write things in Python. You could use p-range here. You can see I use p-range here, and I could decorate this thing with parallel, and this runs, if I run these bits of code, you can see that if I run, this is my implementation of sum on the axis 1, and if I run this, you can see that on the bottom it uses all my cores, and it's parallel. The fun one is, so if you don't want to implement your own ad, the fun one is PyTorch. And PyTorch has many operations. And the thing is, you can see here that torch that adds array here. It doesn't make a copy. It looks at your NumPy array, existing NumPy array. It looks at calling as array on the PyTorch array creates a PyTorch tensor, and that is just a view into the underlying memory of the NumPy array. And so no copy. You could call sum on it, and then you can return it back out as a NumPy array. So if you want to stay in NumPy land, this is a quick way to accelerate sum. And if I run this code, you can see that PyTorch is parallel by default, which is a different characteristic than NumPy. So that's a very quick way to parallelize addition in this case. So that's a demo. So we touched PyTorch. PyTorch is parallel by default, as you saw. It's built on OpenMP or MKL, and it has environmental variables for configuration. It also has a library-specific parameter called torch.setNumThreads, so you can set number of threads for PyTorch. So you're going to see many different patterns come up again when it comes to configuration of these libraries. There's environmental variables, there's some library specific function for doing this. Okay, so that's NumPy. That's it, and that's a different NumPy. SciPy also has some parallelism. It does a little more. It's not only OpenBlast. It covers linear algebra. So SciPy has its own linear algebra. SciPy also uses multiprocessing and multithreading in smart ways. And it has its own custom C++ thread pool for other functions. So it uses a broad range of methods for parallelizing Python. Linear algebra, quick one, same semantics as NumPy. It dynamically links to a blast, and all the same configurations you had in NumPy is in SciPy. Multiprocessing is a fun one. It's configured using the workers parameter, so it's at the call site. And these are the 4 functions that does multiprocessing. You have to look at the code internally to see how it does, but these are the 4 functions. Why does these functions use multiprocessing and not like multithreading? Well, for example, brute.optimize accepts a user function called func over here. Here, func. So you don't know if a user releases the GIL or not. So the safest way, the way you know for sure that you could parallelize this code is to use multiprocessing, because multiprocessing spawns multiple processes that has its own GIL. So this works around the problem of the function will still need to hold on to the GIL. So this is why this is multiprocessing. So multiprocessing, if you're not sure if the function you're trying to parallelize releases the GIL or not. On the other hand, there is multithreading in SciPy. It's all in the spatial trees, KD trees specifically, also configured using workers parameter. And this is using multithreading. And the reason why this could be use multithreading is because the routines that that the spatial trees are trying to parallelize in the query method is written in C++, which releases the GIL. So when the GIL is released, you could run multi-threaded, and since there's no GIL, since all the threads release the GIL, they could run in parallel. And that is why this is multi-threaded. All right. I covered a lot here, but those are the big overarching ideas about multiprocessing and multi-threading. There's a few bits more here about shared memory, which we'll cover in a later slide. And in general, multiprocessing, you have to think more about start methods. Multi-threading, there's one way to think about it, but multi-threading, you need to think about the GIL. Because you need to make sure the things you're parallelizing releases the GIL. And a lot of things do. Like NumPy usually releases the GIL. So, but you have to be sure of this, though, when using multi-threading. So, first, SciPy. There's also things about shared memory, which where multiprocessing, you have to pass memory around, which I'll get into in another bit. Okay, SciPy also has C++, using thread pools and with its own custom pthreads, and this is very focused on its FFT module. And it's configured using workers, just like everything else. This is written in C++, so it could use native threads for parallelization. So one fun question to ask here is, why is it using pthreads and not another like threading library like OpenMP? This is an issue in SciPy that this question was asked on an issue, and like when developing FFT, OpenMP has interesting little issues when you have period. For example, GNU OpenMP is not fork safe. So it doesn't work well for one of the start methods in multiprocessing. But LLVM OpenMP is fine. So like it's kind of, the story is kind of, it doesn't work well all the time. And there's OpenMP libraries running simultaneously may not be compatible with each other. And so we'll get into this a little more in the future, but this is the general idea of why SciPy uses pthreads and not OpenMP. And OpenMP is another threading library that one can use. Okay. Pandas. How many people use pandas here? All right. Pandas parallel, maybe? Question mark? How many people? There is a little bit of parallelism in pandas, and it has to do with how you could have a Numba engine for pandas. And these are in the group by enrolling aggregations. And it could parallelize over data frame if you set the right keyword parameter. So I think this is interesting enough to have a demo about pandas and parallelism. All right. So here, pandas. I'm creating a data set of 1 million by 10 columns. So this is my data set. And I'm going to create a data frame, and then I'm going to do a rolling window. All right? Straightforward pandas, and I'm going to call the mean. So I'm going to find the mean of the rolling windows. So if I time it for row.mean, you can see that 1 bar would light up on the bottom. So 1 bar at a time. So this is single core. If you want to parallelize this, it's the same call, but you pass in a little more arguments. You pass in engine equal number, and engine keyword arguments equal to parallel. Engine arguments with dictionary or parallel true. And if I run this, you can see that it will use all my cores. So I just pass in few arguments and then parallel, and it runs faster than above. So this is a quick way to parallelize your Python, your pandas code for the functions that support it. All right, so pandas, and that's it. And that's the only way to parallel. That's it. That's how pandas is being parallel. They're looking into thinking about integrating OpenMP or pthreads into the library, so it's parallel by default. But that is not in pandas now. Speaking of Numba, there's this fun library called UMap. How many are familiar with UMap? It's a fun dimension reduction library. It's all Python, and it uses the Numba decorator to parallelize all the code. So that's a quick, fun mention on UMap. So I'm throwing Numba a few times here. So configuration for Numba. So there's many libraries that use Numba as a way to parallelize their code. And the way to configure Numba in all these cases is that they have an environmental variable, and they have a Python API as well. Numba, that's not NumPy. It also has many backing layers. It has OpenMP as a threading layer. It has Intel threading building blocks, PPP as a backing layer, and it also has its own custom thread pool if you don't have the other two installed. Now, there are some considerations when using Numba, and Numba has thought about this stuff, where when you're using certain types of threading layers, it may not be compatible with how with certain Python parallel libraries. And there's different flavors of multiprocessing, as you saw before, and multithreading. Not get too much into it here, but in the NumPy documentation, they cover this through and through. So you have to be careful with how Numba, for example, when you run gnu OpenMP and you fork, Numba will catch that and be like, no, you can't do this, because it will stall indefinitely. So Numba will catch and raise an error so that you as a user don't have to worry about it. And then I like this approach for Numba. All right, so I touched on Numba here. And I touched on like C++ code. And this falls into two big camps of parallelization. There's ahead of time compilation and Numba, which is just-in-time compilation. So languages like C++, Fortran, Rust, Cython, you have to compile it first. And you have to, if you want to parallelize your code, you have to choose, most likely choose between these two. Ahead of time compiling means that it's harder to build. You have to actually compile your code. So you have to set up a whole build system to distribute ahead of time compiled code. But the nice thing about this is there's less requirements at runtime. A user would just install, runs. Numba is nice because the source code is Python. Like as we saw before, you could just write normal Python, add the Numba decorator, parallel. But the downside is that it requires being compiled at runtime because it's just in time compiled. So those are the options you have to weigh. As it ashes here, Numba does have ahead of time compilation. It's just not as full featured as just in time compilation. So that's these two things. I mentioned Rust here. So what's a fun library that's new in Python that uses Rust? Polars. All right. Polars is parallel by default. You run if you compute with polars, it just uses all the cores. The way it implements parallelism, it uses a Rust library called Rayon, which underneath the cover uses pthreads. And the way you configure this is polars max numthreads. So polars. Okay, scikit-learn has parallelism. It has many fun forms of it. Like SciPy, it uses multithreading, multiprocessing, but with a fun Loki backend. It has OpenMP routines, which is parallel by default. It also inherits all the blast semantics from NumPy and SciPy because NumPy and SciPy are dependencies of scikit-learn. So if you're a library that uses NumPy and SciPy, you also inherit all the parallelism aspects of using BLAST, which is all the linear algebra operations. Okay, multithreading. Multithreading is used famously in the random forest. This works because random forest is written in Cython, and the Cython code releases the GIL, which means you could do multithreading. So that's multithreading. The configuration is use njobs, and that configures it. Okay. Multiprocessing. It's in our famously in our parameter searching, hyperparameter searching estimators. A fun new one is having grid search CV, which is our successive halving implementation. I recommend looking into that. And the configuration here is also njobs. The reason why this is multiprocessing is because you don't know that the machine learning model you're using will release the GIL or not. So you're stuck with multiprocessing here. So multiprocessing uses something a few scikit-learn developers developed called Loki, which is Python multiprocessing, but better. Right? It has some certain features like it detects when worker process fails and then raises an error in Python. It reuses pools of workers. It spawns by default to avoid the whole OpenMP doesn't work when multiprocessing forks. So it tries to make it so that it's easier to use multiprocessing, basically. As I said before about memory, when using multiprocessing, you have your main worker, which it could be your Jupyter notebook. It has data, and then spawning all these workers to do some computation. And this, by default, the data is pickled and copied onto these workers to do computation. And that bloats if this is on one computer, it would use up your RAM, basically. What scikit-learn does is that it writes your data to this as read-only. And this is a very common paradigm with other frameworks that do multiprocessing. It writes to this as read-only data, and your workers just references that data and then computes on it. Which means that the workers just reference one single references data, which means it doesn't copy it to each worker. And this is using memory mapping. That is mem mapping. So when using multiprocessing, you have to think about the memory. And this is the solution that scikit-learn came up with. Can we questions then? Yeah. Okay, we covered OpenMP as well. Scikit-learn has OpenMP, which is parallel by default. I want to highlight histogram grading boosting, which is scikit-learn's like GBM implementation. It uses OpenMP. Recently, we have pairwise distance reductions that use OpenMP by default. And many estimators and machine learning models use this. So there's tsne, there's k-neighbors, there's a lot. And the way you configure this, since it's OpenMP based, is OMP threads or threadpoolctl. Okay, so we're quite a bit here. We did multi-threading, multiprocessing with Loki. We did OpenMP. Now, what if we combine them? Like, what if we do multiprocessing and OpenMP? Scikit-learn has developed its backend uses joblib, and it automatically detects how many workers you're spawning, and then configures the native library to use the correct number of threads, so that you do not run into oversubscription. This is demonstrating. I wanted to create a demo on this, but as you can see in the slides, it takes too long for the oversubscribed part. So as a quick example, here the classifier is histogram grading boosting, which uses OpenMP, and having grid search CV, which uses Loki. So this is nested parallelism. There's parallelism in the estimator itself, and there's parallelism when searching. And I'm going to measure the time. I'm just going to time a bit. And this is my results. Very quickly, I'm going to focus on certain items. You can see that n jobs equal 1 and OMP threads unset, which is the default. Most people don't set OMP num threads. You can see that it takes 42 seconds, and that's exactly the same as setting it to 16. So by default, if you use one job, so no work is being spawned, it uses all your cores, 42 seconds. It's the same thing as not setting it. Now, if you do n jobs equals 16, and you unset it, you can see that it performs with 8 seconds, which is the same as setting OMP thread num threads to 8 seconds. So it will automatically set the number of threads equal to, in this case, 16 divided by 16, because in this machine I had 16 cores running. And at the end, you can also see that I try to run this with 16 n jobs 16 and OMP num threads to 16. In this case, joblet doesn't do anything because you manually set it to 16, so it's going to obey it. And in this case, I ran it for 10 minutes and I gave up because it didn't work. It didn't end. So this is something to think about when thinking about oversubscription. So this is a problem, and libraries like Dask, they by default when working with Dask, it sets all the environmental variables to 1. So when Dask spawns its workers, it doesn't. It just everything would just be single-threaded mode, and that's how it avoids the oversubscription problem. How many people have heard of Ray? It's a fun new library. Does the same thing. It will also set all these native libraries to 1, to single-threaded, because it has its own way of performing, spawning workers to do multiprocessing. So in both of these cases, it configures its native library to be single-threaded. Now, there's a lot of bits here, and the question when thinking about this talk and thinking about parallelism in Python is there an issue with all the current state of Python and parallelism? Maybe, like, as I said before, when using multiple parallel APIs, things come up. Even if you use multiple native thread libraries, like OpenBlast, when you're using OpenBlast with pthreads and OpenBlast, and then you have OpenMP code, things may stall, maybe. If you're using 2 OpenMP runtimes, which mean OpenMP compiled with LLVM and OpenMP compiled with GNU, things may be bad. And also, if you have 2 OpenBlast present, which is commonly, you commonly see this when you install SciPy and NumPy or PyPI. They both ship with their own OpenMP, OpenBlast. And this led to a performance regression in Mac laptops, machines. But SciPy set an environmental variable to patch things over, which is not great. You have to, the library sets an environmental variable to stop a performance regression. So you can read more. I wrote a lot about this fun stuff in this design document. Also, when combining native libraries, like using pthreads and OpenMP combined with multiprocessing in Python, all sorts of fun issues. There's like every library has its own documentation about this. So like there's like polars, there's Numbas, like learn pandas. They're like, oh, if you use Python multiprocessing and use a library, things may break, but watch out. So that's fun. I like how Numba handles it, like I said before, where it tries to detect these edge cases and raise an error so that a user could properly handle it. Because if a lot of these times the issue is it stalls and you have no recourse. So besides reading the documentation. So it's nice if the library detects these and just raises an error. Okay, the second issue is parallel by default, question mark. This is a question I'm thinking about and if this should be the case. What I mean by parallel by default is some libraries are parallel by default, like PyTorch, or polars, which uses all cores by default. And the other side, they're single-threaded by default, which is pandas. And there are some things lie in the middle, which is sometimes parallel, sometimes not. So what should be the default? Do you want a machine that uses all the cores by default when running or single-threaded. So this is two aspects of this. If you're on your laptop and you want to go and you're doing like something data analysis on your laptop, you do want to use all your cores and you want to get the most performance out of your laptop. So that's an argument for all cores. Single core, people that are putting things in production. Like it's much easier to reason about if your program is single-threaded and then you configure it to be parallel, rather than having parallel by default, because you may have your own way of paralleling your code, and then it runs into the problem with Python also paralleling it. So I'm open to discuss this in detail with everyone, with who has opinion on this matter. Okay. So lots of stuff here, but the overarching themes were configuration, implementation. For configuration, you have environmental variables. We went through a whole skew of them. There's OMP numthreads, there's MKO numthreads, and etc. There's libraries that have Python, that have a Python API to set it globally, like PyTorch. There's also context managers like threadpoolctl that sets it locally in Python. And there's also call site parameters like workers and jobs. There's a lot. Maybe an issue, maybe. Like it would be nice if there's a unified way to do this. But this is so if you're new to a library, you have to know and go through the documentation so you get this information on how to configure your library. That's on the configuration side. On the implementation side, there's many ways to do it. And you can write you can write it in C, you can write it in C++, Numba, Rust, any language you want. The underlying mechanisms is still, you could use multiprocessing from Python and multithreading from Python, or underneath it could use native threads. So the underlying implementation uses one of these parallel mechanisms, but the language may change. So that's the implementation. Okay, so that's a very fast overview on parallelism in numerical Python libraries. All the material is available on GitHub, and hope everyone here now gets a good glimpse of how all these libraries try to run faster on your machines. Thank you for coming to my talk. Yeah, you have a question?
Awesome. Any questions? Cool. Actually, I'll start with, since I have the mic. It's kind of a specific question, but in linear, so in scikit-learn, like linear regression and ridge regression, are those parallel by default since they use like matrix multiplication, I think?
Okay, so I'm like scanning through the code base in my head, so give me a second. During fit, it uses v squared, which from SciPy, or it uses v squared, which is not parallel by default. But during prediction time, yes, it uses matrix multiplication. So it's parallel during prediction time, but not during fit time. Add a few.
Yeah, so I'm kind of new to this, and I wonder what is the difference between multiprocessing and multithreading?
Oh, I kind of really quick went through that one slide that covers it, but multiprocessing spawns multiple Python multiple interpreters, and which has their own GIL. They're usually compared to multithreading, they're slower to spawn. Like it's slow to spawn different processes, while threading, it's quicker to spawn. And there's also other ones. In multithreading, if you're multithreading Python code, you have to, for numerical computing, you have to make sure that your things you're multithreading releases the GIL. Multithreading has shared memory. There's quite a few differences, but for this talk, I try to push that you use multiprocessing if the Python function you're parallelizing over does not release the GIL, and then you can use multiprocessing to parallelize it. But if the thing you're parallelizing over does release the GIL, then you can use multithreading. That's kind of the talking point I was trying to push. Yeah.
First off, thank you. Quick question about Do you know approximately what version of scikit started supporting mem mapping when forking processes? It's not a pop quiz or anything, but it wasn't always like that, right?
Yes. Oh no, no. I have to go through the history of this. It's probably like an early, like 0.22. Okay, it's 0.22-ish.
Pretty good.
But this is a default from joblib, and even if you have an old scikit-learn version and you install a new version of joblib, I think this default turns on. Do you have a follow-up question on this?
No, a separate follow-up. Whether when you were evaluating different strategies, did you consider including like using a context manager with a Dask backend, or is that not a fair comparison because the scheduler is kind of intervening?
Oh, is the question about can you distribute the task using Dask with a context manager?
Well, just thinking about like some of the scikit stuff that you went through, you can start like a local Dask cluster and use the context manager, set that to the back end, and then have some scikit code in there running.
Yes.
And that would be another option. But I was wondering if you omitted it because it's not apples to apples comparison.
I see. I didn't want to put. So okay, so for context, you could. The most popular one is you could run instead. Java uses Loki by default, but you could switch that with Dask, and then run a Dask cluster and run using Dask to polish your code. And I didn't put it in to simplify the talk. I don't want to cover Dask too much.
Any more questions? All right.
The mic
Questions
goes here.
Should I have like a strong opinion on BLAS or OpenMP? Like if I just got a new computer, do I install one, or how do I think about those two?
You use the default, and hopefully, I don't want a user to think too much about this. So use the default provided by your installer, because installers install different BLASs, and if you're the thing I would be concerned with is performance. Like there was a time where the Intel MKO didn't run as well on AMD. And in that case, you may want to switch out your BLAS because of the performance. But besides that, I hope that the default would be fine, and a user won't worry about it.
There is another question.
No, I didn't.
Oh, you do? Okay, yeah.
So Thomas, you showed us that sort of the APIs for configuring the amount of, I guess, workers. There's sort of all over the place. Some people call it workers. Some people call it something else. Do you think that, saying the parameter name should be workers is doing it at the right level, or should there be like a workers and threads or processes, something like that?
This is opinion. I've heard many arguments on this. I do if I was a newcomer, I would want some unified way to do this. Like I think I showed like 7 different ways to do environmental variables. Like call site parameters, there's 2 or more in other libraries. Libraries could have their own call site. Like I do wish like workers would be the parameter we use. If I really wanted, I would wish there's like numerical Python numthreads or something, and then like every numerical Python library just uses that, and then to configure it would be nice, and so you don't have to worry about which backend you use, so that a user would just configure one variable, and it would just work for all the libraries. That'd be very nice, and I do wish for that to happen. But it's a lot of you have to gather support from all these libraries to do it. That's the hard part.
Thank you.
Let's do one more question.
Yeah, is there a good way to figure out whether or not a function releases the GIL or not?
Oh. I don't think so. Okay, the fun way is to create a multi-processing pool and then run it and see what happens.
So it's basically just trial and error.
Yeah. You could use one of the inspection. There's a vis tracer, and you can run vis tracer on it, and then see if it reduces the GIL there. But there's no. It'd be nice to create that library, by the way. Like does my function releases the GIL? So good idea. But it doesn't exist right now.
Cool. That was awesome. Let's thank our speaker again.